Hi everybody, welcome to another video in differential equation, section 4.9, section 4.10, a closer look at mechanical vibration. So what we have is a mass spring system. That means a spring and then a mass. If we pull it down, it will vibrate. So what will affect it? First, mass time acceleration. So of course, that will, when we add up, it will equal to the force of the whole thing. So this is inertia. It's due to the mass. And damping is, think about this, if it's move up and down, the air resistance will slow it down. So this is due to friction. And now, next, due to the stiffness of the spring, what we have here is the restoring force. If we pull the spring down, pull the mass down, the spring tend to get back to the original shape. Or we push it, it will get back to the original shape. So this is due to the stiffness of the spring. So this is due to the mass, this due to friction, and this due to the spring that has the stiffness. And I think last time we have the equation is the mass times acceleration plus the damping factor times velocity plus K is the spring constant times the displacement. All of that will have add together will be equal to any external force. So the system will, all the force will be balanced out. So once again, mass times acceleration, damping factor times velocity, and the spring constant times the displacement all add up to the external force. Now in this section we study about different scenarios of the case where we have the mass, the damping factor, and the spring constant. So let me just write down different scenarios of those. We have different type of differential equation. I should say different type of solution. M of course is the mass. B is the damping factor. And K is the spring constant. Yeah. Right. Now, like I said, we will study different cases of M, B, and K, which result in different type of solution. Right. The first is when we have no damping, meaning that B is equal to 0, and no external force, meaning the external force equal to 0. So this equation becomes just that. And the differential equation in standard form we have in that. And of course auxiliary equation. But first, to make things simple, we will make K over M. K is positive, M is positive. So we can just say omega is equal to that. So this equation, if we let omega equal to square root of K over M, this equation becomes y double prime plus omega square y equal to 0. Auxiliary equation is r square plus omega square, and because the solution will be plus or minus omega I. So we write the solution as this. So this is nothing new here. Right. So what new here is that the technique is very, very old, like in trigonometry or with calculus. But if we have the equation of sine of something and cosine of the same thing, so both of these have the same sine and cos, I mean the angle, the argument will be the same, right? If that is the case, we can combine this into this form. Right. So how do we do that? Well, the trick to do that is, if we write like this, of course we multiply them out, and then so first we'll see we have the properties identity of sine of a sum. So let me write that identity. First, sine of a sum is sine A cosine B plus cosine A sine B. That's exactly what we have here. So what we do is we have, or I should write this in reverse. So we have a cosine and a sine ready. We need to manufacture a sine from here and a cosine from there. So to do that, this is the trick is this. We multiply and divide by square root of c1 square plus c2 square. So we first multiply and then we divide. Okay. First I will multiply by c1 square plus c2 square. Of course we cannot just multiply, we have to divide. So we have c1 over square root of c1 square c2 square. And then we have cosine of omega t. Yeah, so just multiply and divide by square root of c square plus c2 square, and then plus c2, of course divided by that. And then we have sine of omega t. Now, so the reason we do that because c1 over square root of c1 square plus c2 square, this two is going to be, one of them will let equal to sine and the other one will let equal to cosine. Because if we square these two and add them together, let's do that one square. We have c1 square plus c1 square plus, and then we square that, c2 square, c1 square, c2 square. Common denominator, we have c1 square plus c2 square. Now, so that one square plus that one square is equal to 1. And another one that has the properties is cosine square plus sine square is equal to 1. Because of that, we can let one of them to be sine. So let this be sine of phi. I mean this whole thing here, and this one will be cosine of phi, and then that identity will give us a sine of a sum of omega t plus phi, and then we will let a equal to square root of c square plus c2 square, right? So we combine that and we have this equation. And then the phi can be, of course we can do the sine inverse of this, but the better we just do the sine tangent inverse of c1 over c2. So we can combine the equation into one. So the reason when we combine that into one, because when we have one function, it is easier to work with when we solve for equal to 0 and other things. But now if the equation is in this form, the A is the amplitude. I didn't have this, did I? So amplitude. The omega give us the angular frequency. The frequency, the natural frequency is omega over 2 pi. So first, if we're going to graph that function, it is bounded by within the amplitude. Now back in trigonometry, when we have the equation, let's say y equal to sine 3 sine of 5x, for example, if that is the case, the period is going to be 2 pi divided by whatever the coefficient here is, right? So this case, the period is 2 pi divided by 5. If we have 6, that will be 2 pi over 6. So it's going to be 2 pi divided by the coefficient of t, or the coefficient of variable. So there's nothing new here. The period is what we have. The period is in terms of second, so how long a function will repeat itself. A natural frequency, if we write that as an f, the period, if we write that as a t, f and t are reciprocal of each other. You see 2 pi over omega, omega over 2 pi. So frequency is equal to 1 over t. So the period by default is 2 pi divided, default is 2 pi. If we have a coefficient of t or coefficient of x, 2 pi divided by that give us the period. Flip it, we have the frequency. So period and frequency are reciprocal of each other. And the angular frequency is omega, which is square of k over m. Of course, this is only in this case, only in the case where we have b equal to 0 and external force equal to 0. So we just have this equation. That is the equation. This is the solution. And in this equation, we can find the amplitude. So the graph will go between negative a and a. And then the period is a t. So this is a period. Of course, a period is the length. But just say will be this much. That is a period. Of course, you can say the period also can go from this point to this point. The idea is the period is where the graph repeats itself. So if we just have that part, we just copy and paste, we'll have the whole graph. So whenever the graph repeats itself, not only repeat the values itself, but repeat the pattern. So that point, at that point, it's on the top and going down. At that point, it's on the top and going down. So we're not talking about these two to be the period, because this point, even though the y values are the same, but this one, the function is about to go down. This point about to go up. So the period is not counting from there. The period counting from these 2 points because they have the same y values and both of them tend to go in the same direction. So the pattern repeat for every length this much. Right, so that gives us a period here. And then the graph will start at this point, which we define to be a phase shift. A phase shift is easy. If the equation is sine omega t plus phi, we're going to let that equal to 0. So we're just going to let omega t plus phi equal to 0. So the phase shift is equal to, the phase shift is phi equal to, sorry, the phase shift is not phi. The phase shift is due to result from pi, I mean from phi, but the phase shift is going to be negative omega, negative phi over omega. So this is where it starts. That is the phase shift. And then the sine function, of course, is a wave line. So that's what we have from that equation. Right. Let's look at one example and see how that works. A 1 over 8 kilogram mass, so the mass is 1 over 8, is attached to a spring with the stiffness or the spring constant. It says 16 Newton per meter. The mass is displaced 1.2 meter to the right, so we pull that to the right. And given an hour, so we're going to, not only we pull, we're going to give the force, pull that to the right at square root of 2 meter per second, neglecting any damping and external force. So assume that no damping or no external force. So B is equal to 0, external force equal to 0, mass equal to 1 over 8 kilograms, and spring constant 16 Newton per meter. So we have all the equation. Now, let's do the first part. I'm just do both parts at the same time. So the equation. First, let's write the equation. M y double prime plus by prime plus ky equal to the external force. In this case, we have, of course, no damping and external force equal to 0. So in that case, and we have the mass and the spring constant, so we have 1 over 8 y double prime plus 0, and k is 16 y equal to 0. So that is the equation. What else do we have? Right. Originally, the mass is displaced 1.2 meter to the right of the equilibrium point. So what that means is our initial position is going to be 1 over 2, which is 0.5 meter on the right, so it's going to be positive. If it is on the left, it is negative. And not only that, we give an hour velocity. Not only so, we have the spring, and we pull at 1.5, and then we pull one more. Just give the kind of initial velocity is square root of 2. It is also positive because it is to the right. So we have this is the equation and the initial values condition. So we have initial value problem. Prefer that to IVP. Now, of course, we can solve this. This is easy. From here, we can write the auxiliary equation, and then we solve for the solution. Should be simple, right? So, auxiliary equation. One over 8 r squared plus 16 equal to 0. So we can solve for r squared. Be negative 16 times 8. Negative 16 that's negative 128. Take the square root of that. When we take the square root, there's plus or minus on both sides. Negative inside the square root, so that is imaginary. So we say r equal to plus or minus. So there's an imaginary here. And then square root of 128 is square root of 64 and square root of 2, right? 128 is 64 times 2. Take the square root. So 8 square root of 2. Because of that, we can say the solution y1 equal to cosine of 8 square root of 2 t. y2 is sine 8 square root of 2 t. And put them together, the complementary solution. In this case, also general solution, because we don't have particular solution for the homogeneous equation. So y equal to c1 cosine of square root of 8 square root of 2t plus c2 sine 8 square root of 2t. Right. Now, the initial condition, y of 0 equal to 0.5. So y is equal to 0.5. Equal to c1 cosine of 8 square root of 2 times 0, because t is equal to 0, c2 sine 8 square root of 2, 0. Sine of 0 is 0, cosine of 0 is 1, so we just have equal to c1. So c1 is equal to 0.5. Right. Next, we take the derivative and the initial condition for derivative. So first we take derivative. We know c1 is equal to 0.5. If we want to, we can just go ahead and do that, but it doesn't matter here. Just take derivative. Y prime will be equal to derivative of cosine is negative sine, and then we take derivative of the angle, so a square root of 2 c1 sine 8 square root of 2 t plus 8 square root of 2 c2 sine 8 square root of 2 t. Now initial condition, derivative equal to square root of 2 . So that's why I said we don't need to put c1 here, because here we have 8 square root of 2, t is equal to 0, so the whole thing is 0 anyway. This is equal to 0. 8 square root of 2 c2 sine 8 square root of 2 times 0. Sine equal to 0, cosine of 0 is equal to 1. Right. So of course from here we can get c1. So c1 negative 8 square root of 2. I got them backward, did I? Sorry. The sine is equal to 0, and no wonder. Okay. Derivative of sine is cosine. Sorry, did I? Okay. This is the function. Derivative of cosine is sine. Derivative of sine is cosine. So this will be cosine. Sorry about that. Right. And cosine is equal to 1. So I have 8 square root of 2 c2 equal to square root of 2. Divide by square root of 2 and divide by 8. So c2 is equal to 1 over 8. Oh, we can write 0.125. Yeah, that's 1 divided by 8. Right, so put them together, we have equation. Right, y equal to c1. c1 is 0.5 cosine a square root of 2t plus c2 sine a square root of 2t. So we have the solution. Now what we do is It's just like what we did earlier. We try to combine this into one function of sine. So in that case, if we want to, we multiply and divide by square root of 0.5 plus 0.125 square. So first we multiply. And when we do that, we have to divide. And then sine 8 square root of 2t, right? Now let's get the values of that first. Square root of 0.5 square plus 0.125 square. That is 0.5154, right? And now we can let one of them to be sine, one of them to be cosine. So we can combine them together and we have the equation is that sine of eight square root of 2t plus 5. And because if 5 equal to tangent inverse, tangent is y over x, right? So, or sine over cosine. So sine over cosine. Yeah. So sine over cosine is equal to tangent. And what is 0.5 divided by that? So I think it's 4. That's 4. So with tangent inverse of 4. So we have the equation. So from here what we can get is the amplitude (0.5154). The period is 2 pi divided by the coefficient of t, and the frequency is the reciprocal of that. Right. The period is the time that takes for the function to repeat itself. I'm not talking about just the y values repeat itself, I mean the pattern repeat itself. So in that case, the period is second, frequency is 1 over second, the amplitude will be whatever the unit length, so let it be meters. So if we move it, so the object will vibrate and the magnitude is that much. I mean the amplitude is that much. Right. So how long after release did the mass pass through the equilibrium? So meaning that we're going to let this equation equal to 0, right? So we have this equation equal to 0. So we say the mass at the equilibrium because when we talk about mass, we mean consider the big mass is it's just one point. So we talk about point mass. Consider the whole object is located. The mass will locate at just one point. We're not talking about the big object, that's different. Right. So we're going to let this equal to 0. That is c plus phi equal to 0. So meaning that a square root of 2 t plus phi equal to 0. So we can solve for t, sorry, because we know phi is tangent inverse of 4. So t equal to what? Sorry. But the problem is when it equal to 0, and it not only that what we have, because in the unit circle we can say it plus k pi, because sine equal to 0 at these 2 points, right? So we just solve for t. So t equal to k pi minus phi over h square root of 2. Now just choose, if k equal to 0, t is negative, time cannot be negative, right? So that's why we cannot choose t to be 0, otherwise it will be negative. Tangent inverse of 4, keep that in range, yes. So tangent inverse of 4, it's going to be that, it's going to be positive. So if k is 0, that is negative, it doesn't work. So the first time it will pass through the equilibrium is, let's say, what happened when k equal to 0? I mean at k equal to 1. At k equal to 1 we have pi minus tangent inverse of 4 divided by a square root of t. Square root of 2, sorry. Yeah, that. So that is after 0.16 seconds, the object will go back to equilibrium. So about 0.16 seconds. Right, so that's what we have. Let's look at the different example. Now, suppose a spring is stretched at 1.5 inches by a 2 pounds weight. So the spring originally will be stretched 1.5 inches. Because if the spring by itself, it just by itself, and then we stretch it, the weight causes it to go down. And then let the weight be pushed up 3 inches above the equilibrium. And then release. Write the equation that describes motion. So first, the problem here is the 2 pound weight. The weight is not the mass, right? The mass is constant. So let's say if the mass of 10 kilograms on Earth is still 10 kilograms, that 10 kilograms in the space, in outer space, where there's no gravity, is still 10 kilograms. But because of there's no gravity in the outer space, the weight is going to be 0. So the weight depends on the gravity as well. So in the moon, it will be about 1/6 of that, of the mass. So the weight in the moon will be 1/6 less than what we here on Earth. But the mass is still the same, still 10 kilograms on the moon, or in outer space, still 10 kilograms. But the weight will be different. So the weight is equal to the mass times the gravity, acceleration due to gravity. And let's assume that it is on the surface of the Earth. It is about 32 feet per second square, or it is negative 9.8 meter per second square. But because we use the English type unit, so we use 32 feet per second square. Right. Yeah, of course, like I said, assume that it is on the sea level. if it is not on the sea level and it is like further away from the center of the earth, the gravity will change. Right. So in that case, we divide this, we have 1/16, and the unit for mass in the English unit is called a slug. And the Hooke's law, we do the same thing, and that's what we have. So we have the equation, because they didn't say that's the damping factor, and then I know. And then let the weight be pushed up 3 inches above in equilibrium. So the position at 0 will be 3 inches. We can say it, let's assume that it is above, so it's going to be positive. And we just push it, and then we hold it, and then release. So we did not push, we did not give it any initial force or initial velocity. So that's why we have this system. Oh, sorry. This system, I want to rewrite that. So initially it is 3 inches, but we write that in feet. And of course we can let that to be negative or positive. Depends on what we let it. So we're going to push equilibrium. Let's say originally it is here. So we're going to have, so we can define up is negative 1.4. I mean 1/4, because 3 inches is equal 1/4 feet. So foot. So the unit here is foot and inches. So we have to write everything in terms of that. Yeah. And it is stretched by the 1.5 inches by the 2 pound weight. So the 2 pound weight we stretch 1.5 inches. 1.5 inches is equal to 1/8 feet. So the unit will be in terms of feet. So we put that in for x, and we have that. Right. Now, of course, if we equilibrium, if we consider this direction above it is negative, then of course that's going to be negative. If of course we can let that to be negative too, so I just make it consistent. If we can just keep on the top to be positive or the bottom to be negative, in that case just it will be keep things consistent. Right. So that's what the equation is. Of course we can solve for that and did exactly like we did before. Now let's go to different scenarios of this equation. Now suppose that this is the damped mechanical vibration, meaning that B is no longer 0, so B is going to be positive. And suppose, first of all, suppose that there's no external force, but there is the damping factor. So we do that, we define delta. The reason we call that delta, this is the discriminant. Of course, the solution auxiliary equation is negative B plus or minus B squared minus 4AC. In this particular would be minus 4 MK over 2M. So the solution for this quadratic equation, auxiliary equation, is going to be that. So that's why we determine the part that is inside the square root. So from that equation we have auxiliary equation, and the solution is going to be in this form, right? Now, if inside the square root is negative, that means we have two complex solutions, right? Negative inside the square root, imaginary solutions. I mean complex solution. And we're going to write the solution like this. And then of course we combine the sine, cosine, and of course the solution. That's why we write it's like this. So in this case, what we have for different is going to be the E alpha t. Notice that alpha would be negative b over 2m. I should split this in two. Okay. Try to write that. This, if I write here, equal to negative b over 2m, that is the real part, and then plus or minus square root of b squared minus 4 mk over 2m. That part we have imaginary because there will be negative inside the square root, but the real part is negative b over 2m, and that's what we let equal to alpha. So we have exponential damping factor a times a to the alpha t is going to be equal to that. Now notice that for this equation, as t equal to 0, this go to 0. Let me just write limit as t goes to infinity e to negative b over 2m t equal to 0. B is positive, m is positive, so we have negative here. That is equal to 0, right? Because exponential function go like that. This one has the negative exponent. Negative exponent, we can bring it down. And become positive. Now this goes to infinity. 1 over something goes to infinity is 0. So that's why we have this case kind of the amplitude. But one of them is a e alpha t. The other one is negative a e alpha t. So the graph will bound between those two exponential functions. And we still have the phase shift here. The period is a little bit different. The period, we can go from here to here. So that is a period. And here to there, that also a period. So actually those will be the same. Those will be constant. I call the quasi period because it is not a simple harmonic function. So, but the period is going to be a constant, 2 pi divided by beta. So you see that's still the same, even though the magnitude changes, but the period is still the same length. So that is the period. 1 over period is the frequency. So that's what we have. So in this case, when we have b squared minus 4mk is negative, we have these scenarios. Sorry, I think I misspelled that. This is not undamped. It is underdamped. Meaning but just undamped. Right. Next, let's consider when it's positive. Now, when it is positive, that means we have the solutions here. When b squared minus 4mk is positive, meaning that we have two solutions, and that we have two solutions. We have two roots like this, and the equation is going to be in that form. Now, the problem is this one will go to when t go to infinity. That equal to 0, because once again we have a negative solution. Think about this. Why the solution? Why the root is both of them are negative? If you have x squared plus 2x plus 3x plus 2. That's 3, my point is, let's say, okay, this one I'm sure. Right, think about this. X has to be negative for it to work, right? Because if you put a positive number in here, there's no way it's going to be positive. If all the coefficients are positive, the solution has to be negative, for sure, right? Because if we put a positive number in here, it's not going to be 0. So if we have B, M, K are all positive, the solution has to be negative. That's what I mean, right? Because the solution is negative, we talk about it. The limit of that will go to 0, right? So limit of something as t go to infinity e to something negative times t will go to 0. So in that case, it will have at most one maximum or one minimum. So if I try to draw it, it might be like just like that. It's not going to vibrate, and we're approaching to 0. All right. Different scenarios, of course, when we have that equal to 0, we have repeated root. Once again, this will go to 0, and the graph will be kind of similar to what we have here. Right. Now, the force mechanical vibration. So this time we have the external force. Let's assume that to be cosine of gamma t. So if we solve for that, we're going to have the equation. The solution is going to be like this. It's not that bad because the real part, imaginary part, we still have the solution there. So the real part times t, imaginary part going to sine, cosine, then we combine, we have this. And if b squared minus 4mk is positive, it can be shown that we can write this equation is equal to this form. Yeah. So b squared minus 4mk is negative. That's where we have a complex solution, right? It's a bit confusing, but when we write this, when I write like this, I mean b squared minus 4mk less than 0. When it's less than 0, we have two complex solutions. That's why we have sine, cosine, and then the real part is still here. So the special thing about this, when we have this type of solution, because we have the external force here, so the input function. So that's why, in addition to the solution here, this is the complement solution, we have a particular solution as well. So that's why we have that. And we have a particular solution. Not only we just have, not only to complementary solution, we have the particular solution too. Right. So, but I'm not sure which, but like I said, right, okay. This is the particular solution. This is the complementary solution because this one has the gamma in it for the input function. Right. Now, in this function, what we have is this term. Once again, this term goes to 0, right? As t goes to infinity, as t goes to infinity, that term goes to 0. Whatever term goes to 0, we call that the transient term. And when t go to 0, when t go to infinity, this unchanged. It still just vibrate. So this is called the steady state. So when t go to infinity, because of that negative b over 2m negative exponent, so that function goes to 0, and this will be just a sign, so it still go up and down. So of course the way it works is after it vibrates a while, the only thing that affecting the spring mass system is the external force, because after a while it will reach the equilibrium if there is no external force. but because of the external force, we keep just going according to the external force. Right, so that is the case where the external force is equal to is not equal to 0. And we have this. Now, on the special case where we have the external force will be the same, I could say, the angular frequency. Now, notice since the solution, the complementary solution, we have omega t, right? And now the input function, the external force, also have the same thing, right? So what happened if that is the case? If that is the case, our gas have to be multiplied by a t to it. Because of linearly independent, we have to have an extra t to it for it to be linearly independent, right? So, and on the special case where the external force have the same angular frequency as the complementary solution, what happened? Right. So when we have that, add these two and combine, we have in this form. So what does that mean? What happened as t go to 0? I mean, as t goes to infinity. As t go to infinity, that one is still a sign, so it still vibrate. But this term, because of the t go to infinity, the whole thing go to infinity. So that's why I just keep vibrating like that. And so this is called the undamped resonance. So think about this. We see this on movies. If we have a glass of water. If we put the right frequency to it, it will break. Because original glass, if we put some sound wave or sound wave properties, it will vibrate. Of course, the vibration will depend on the type of glass and the mass, and of course all the different constant of a glass, right? So the glass will vibrate. Now if we adjust so that the input function, if we can adjust so that the sound wave will have the same frequency as the glass, it will break because this system just keep going. So the glass will vibrate more and more and eventually will break. So if we want to break a glass, it's not that we're going to put a very high sound to it or very low sound to it. The key here, we try to put the right frequency, the same frequency as the vibration of the glass. If we have the same frequency as the input function, as the complementary solution, we have that term, and that term will go to infinity because of, like I said, we multiply by t to it, so make it linearly independent, and eventually when we multiply by t to it, it will go to infinity as t go to infinity. So that I thought it is interesting case. Anyway, so that's what I want to go over these two sections. The point here, of course, I just want to go over some application problem. But the idea, of course, you still need to know how to solve the differential equation. That's why we spent the whole chapter doing it. Anyway, I'm going to stop the video here. As always, thank you for watching, and see you in another video in differential equations.